Okay, so this is the proof of the power rule, and it's not really a proof. The proof gets kind of crazy with the notation, so I'm going to do more of a lead by example, follow the pattern kind of a deal. So here we go. Here's what we're trying to prove, that f of x equals x to the n, then the derivative of that is n x to the n minus 1. And what I'm going to do here is I'm actually going to run through a couple of examples. We're going to look for the pattern, and I'll see if we can kind of decipher how the pattern leads us to this conclusion. So if you recall, the derivative is the limit as h goes to 0, f of x plus h minus f of x over h. So if I take this a little bit further, minus plus h squared minus x squared over h, lose the x squareds, factor out an h, and that leaves us with just a nice clean limit. H goes to 0 of 2x plus h. We substitute in the 0 and we get f prime of x equals 2x. Looks like it fits our conclusion. Well, we really can't just trust it with one example. So let's do one more and see if we can make some sense of this thing. What if we had x cubed? This one's not as nice because we have to go x plus h cubed minus x cubed over h, and I need some room on this one. We talked about cubing a binomial yesterday, well, a couple days ago, and it looks like this. If you guys know of something called Pascal's triangle or the binomial distribution, this little pattern should look familiar. If not, you can Google it. It's kind of a cool little pattern that you can use to distribute binomials. Anyways, it's going to look like this, and what's going to happen on every single one of these is those are going to go, and it's going to leave some combination here, and this h is going to take out that h, one of those, and one of those, leaving 2. Now what's going to happen here is when we plug in the 0 now, I'm going to lose this term because I'm plugging in 0, and I'm going to lose this term. And it's always going to leave that second term, just like it did, just like it did back here. It left the second term, which was 2x. It left the second term here, which is 3x. And as you can see, the exponent, the degree, is reduced by 1 on that term, on that pattern. Similarly, if we were to look at x to the 4th, if I was to expand x to the 4th, I would get x to the 4th plus 4x cubed times h plus blah, 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 and we'll go on forever. And once again, I would be able to lose the x to the 4ths. There'd be 1 at the end. The h's would reduce everything except for this second term, which the pattern is going to have that 4. X to the 5th would have a 5 there, and so on, and the degree gets reduced by 1. So it's not so much a proof. There are proofs, and the notation gets a little tricky and confusing, but the proof is really showing this pattern. So, I don't know. Hopefully you found it interesting. I do. I thought it was pretty cool. And those of you who did watch this, this is a pretty cool site, Wolfram Alpha. And it's a great place to go if you want to find out some research on anything math or physics related. So for example, you could take a peek at Pascal's triangle, and it's going to give you quite a bit of info here. Talk about it. And let's say you wanted to find a derivative of x to the 4th. pretty slick what it does. Gives you lots of info, shows you some steps on how to get there, graphs. Pretty powerful website that you may want to check out this year. I definitely will start referencing it in class. So anyways, have a great day and see you Monday.